Yes, it's all set right now.
Okay, thank you. So, welcome everyone to another seminar in sustainability for systems. We're very happy today to host Tilmann Rabl from the Hasso-Plattner Institute and the University of Potsdam in Germany. So, Tilmann's research focuses on data processing and management in large systems, on modern hardware, and streaming applications. And besides the energy efficiency improvements, which he will talk about today, he's also interested in making systems more user-friendly and friendlier for the environment. So, Tilmann, I'm very happy to host you. I'm so curious to hear your talk. The floor is yours.
Okay. Juana, thank you very much. It's my pleasure to be here. Thanks a lot for hosting this talk. And so let me maybe start with saying that I've always been interested in sustainability and ecological, let's say, friendly behavior. And for a long time, I didn't really find a good way to tackle this in my research. So a lot of the research that I felt like I did some scaling and scheduling stuff, but I often felt this is, let's say, it's very brittle. So it's very easy to do stuff wrong. So and then recently, I've tried to get into a way, and I've found a bit of a way to figure out how can we do things better, right? So how can we improve the efficiency? I mean, generally, right, efficiency is always something that we're striving for, but how can we also look at this from an ecological angle? Will try to kind of tell you what my motivation is and why I think this is important, and to some degree what we can do. I mean, it's not a perfect solution, so you'll see there's still stuff to go, and I have a few points of discussion in here. And with that, I mean, let me also add, if you have a question, right, or if you want to discuss something, or if you want to challenge some of the things that I'm saying, feel free to do so right away, right? I'd rather spend more time on discussing than on just like silently presenting, although I know in an online context, this usually is the case. Okay, with this, let me get started and talk about efficiency, right? And because typically efficiency is something, I mean, we all claim we're kind of trying to build efficient systems, but you can make a difference in between performance and efficiency. And efficiency is something that I would claim you can measure in the resources needed to perform a task. So how many resources in general, from a very abstract level, do I need to perform a task? The lower the resources that I need, the more efficient my system. And that's different from performance, right? So, and this is the thing that for a long time, I was all about, or a lot of my research was mainly about performance. And the thinking is the more performant something that I do is, the more efficiently automatically also is. Because if I finish my queries faster, if I do my LLM inference faster, it really probably uses less resources. But it's not the same thing. It's not the same goal, right? In performance, we usually say how much task can I do, or how fast can I do a task with a given resource, or just in general. And the just in general is kind of the tricky part, right? And in systems research, we often scale our task to the resource. So we basically get like a good efficiency just by tweaking our task in a way such that it fully fills our resource, and then everything is nice and fine. In real life, this is usually not possible, right? In real life, you have a task that you need to do, and ideally, you would do it with the least amount of resources that you can, rather than just whatever you have, or just buying the beefiest server, for example, to run your server on. And let me give you an analogy with cars, right? So that's often easy. I mean, we know all these examples of how cars are, I don't know, differently manufactured than software, etc. But this also holds true for performance and efficiency, right? So if we think about the way we often think about performance, and this is a slide that's more or less borrowed from Gustavo Alonso. If you think about performance, a performance question is how fast can I transport a certain amount of cargo over a certain distance, right? So if I say I have 200 kilograms of cargo and I need to transport it over distance S, if I use a truck, I can do it in a single trip, and a truck would drive 80 kilometers per hour. If I take a supercar needs 3 trips, right? So probably cannot do the whole 200 kilograms of cargo. I will need to do 100 kilograms, drive the distance, go back, pick up the next 100 kilograms and drive the distance again. Needs 3 trips, right? So now the question is this better? And we can simply optimize for this, right? If our speed ratio is in a way that the supercar is 3 times as fast as the truck, then we can choose either. From a performance perspective, this is fine, right? So the supercar drives 3 times as fast, back and forth at 240 kilometers an hour. We choose either. In Germany, we can go 417 kilometers an hour on an Autobahn. So in generally, we of course are better off taking a supercar because the performance is better. And this is the thing often, like if you think about research papers that talk about efficiency or performance, this is the kind of comparisons that you have, right? So basically, you're just using the fastest, whatever is available, you're getting the best performance, and then you claim this is efficient. But of course, for a car, everybody will immediately see, well, this doesn't really make that much sense. And I mean, for a long time, it would, to some degree, make sense to just use whatever hardware you can get because newer hardware is better and it's more efficient, right? So this is something that a lot of the systems building, like it's a general premise that we're basing a lot of our work on. But today, if we look at hardware, it's not necessarily true anymore, right? So hardware performance is not simply increasing anymore. So this is a plot. You might have seen this already. This is the microprocessor trend data. So over 50 years, basically, how did microprocessors evolve? You can see here the number of transistors on microprocessors. And this is basically what you can see is Moore's law, right? It still kind of works. You get and here an exponential increase of transistors per processor. And this, it's important that we see here, this is a logarithmic scale here, right? And this is not something that we did. This is like an already older collection that was extended at a certain point by Karl Rabl for some time, and you can basically find these numbers. You can find this plot online. I just took the plot and then basically ripped it apart so you can see the individual parts. And I mean, while we see still the transistors, we get more and more transistors still on our CPUs. What we can also see is the amount of power that goes into these CPUs is kind of flattening out. So we don't get the same amount of power, like power increase that we had in the past. And the power increase that we put into a CPU, like in order to get better performance, this is mainly utilized to get a higher frequency, right? So in the past, you would basically just add more power, get a higher frequency on your CPU, and this means you automatically get faster processing. And this very much drastically stopped in the mid-2000s, right? So this is, you can see, like for sometimes it's really also, I mean, it's again, exponential increase, right? So this is basically the amount of increase of frequency that we get in CPUs. And this completely halted, right? So here we're now at like a 4 gigahertz, something like this. You might find eventually something higher than that, but that's basically a limit. And this is due to voltage leaking, right? So all of a sudden, CPU manufacturers figured out, well, if we build CPUs that utilize much more power and have much higher frequency, all of a sudden we're losing so much energy. The cooling is so much more expensive. It doesn't really pay off anymore. And this is where then multi-core CPUs came in, right? So all of a sudden, instead of just increasing the performance for a single chip, for a single core, multiple cores came in. and at the same time, the frequency of those stayed the same, right? So there's basically not much improvement here anymore. So, and this also means on a single thread performance or a single thread, you don't get much performance improvement. You really have to change your system, because overall, while we had, like, again, exponential increase in performance, the single thread performance kind of flattens out, right? So you get like slight improvements. This also comes from, as you can see, slight power increase that we have, and some architectural changes, right? So you see some kind of tweaks in the hardware that makes the system still a bit more performant, but not in the same way as in the past. And this also means in general, right? So while we had like higher increase in performance, higher increase in transistors in comparison, like to the power that was utilized, we're kind of in a stable situation. We don't get these kind of performance improvements anymore. And this will also show, right, that, or I'll show in the course of the slides, that like the hardware is not getting much better anymore. And in the end, the software basically probably also is not getting much performant anymore, right? So there's basically what kicks in is, or what always has kicked in, is Wirth's law that you might have heard. It's not really a law. It's basically a saying, is that software is getting slower more rapidly than hardware becomes faster. And at the same time, we see the performance of hardware is not increasing anymore. So all of a sudden, we're in a problem here, right? So what happens when hardware does not become faster anymore, not any more efficient? Then what do we do? So we need still, right? The software gets larger. We get more tasks that need to be done, all these LLMs, etc. All of a sudden, we have to somehow still increase our compute capacity. And what can we do? There's basically two ways to get additional hardware performance. And the one thing is size. So chips are basically, like, in order to have more computation, you can just have larger chips. This is basically an M1. It's like the first ARM chip out of Apple. It's also I'm always showing this because my laptop has this, right? It's 120 square millimeters. If you need more compute power in the same generation of CPU, you buy, instead of the M1, you buy the M1 Pro. That's approximately 2 times the size. And you get better performance, right? So this basically has 4 performance cores here. This one will have 8 performance cores, something like this, right? So it's like different kind of, it's the same kind of architecture, has the same kind of things in there. They're just replicated more often on there. If this still is not enough, you go for the max. Same thing again, just same circuitry, more replications of the same circuitry. And that's not even the end. There's even an ultra version, which is really just basically this thing twice attached to each other. So you get kind of almost 8 times the size of the original M1. So you're just doubling and doubling. So that's one way of getting more performance. You get more compute into a chip by just adding more hardware, right? You just add like more silicon, essentially. The alternative is terminal density power, right? So we said it's kind of stable, but it's also not really true, right? So while you can see my M1, this is a max version now. For that, I could find the numbers. So the M1 Max, and this will probably be similar to the one that I have in my laptop. Here, the maximum thermal density power, the maximum, or the thermal density power, is basically the maximum power draw that the CPU will take, right? So this is at full utilization, how much power does the CPU take? And this is, for this one, it's 92 watts at a size of 430 square millimeters. So per square millimeter, so each individual square millimeter will have 0.21 watts of thermal density power. As a comparison, if you have a modern GPU, right? So this is not the latest, but close to the latest GPU, an H100 from NVIDIA. This one draws 700 watts of thermal density power, has 840 square millimeters, so it's roughly twice the size of this chip. and has a thermal density power per square millimeter of 0.86. So 4 times the amount of power at the same kind of density, right? So you're really powering this with much more energy, or 4 times the energy. And now again, like, I know these are kind of cheesy comparisons, but I still think it's kind of surprising if you think about it. This is like a standard hot plate. And this will be around about the same in Canada as in Europe. So, and if you have like your stove at home, this is about the amount of power that it draws. You have like 1500 watts at 180 millimeters diameter, so 25,000 square millimeters. And here the thermal density power is 0.06 watts per millimeter, per square millimeter. And now you have to think, right? So if you think about how hot this thing will get, if you turn this up at the 1500 watts, this can go up to 600 degrees, something like this. And chip like this needs to be below 80 degrees. So, and at the same time, while you're basically powering this with 16 times the amount of power, you will have to cool it down to 80 degrees to not like melt and break right away. And so this is basically, so what we're basically building there is like really, really hot plates that then need to be stayed need to stay at 80 degrees in order to not melt away right away. And so if we look at this from a larger perspective, right? So from a data center perspective, on the one hand, we see that data centers are actually getting more efficient, right? So this is what if we think about Google, Microsoft, etc., all the major cloud providers, they will show you something that's called the PUE, the power usage effectiveness or power utilization efficiency. And this is like basically showing for the Google data centers, and you will see similar plots for anybody else, right? So I just took this because it's easy to find on the Google website. You can see over the years, this is getting better and better, right? So this is basically how much the power utilization efficiency or power usage effectiveness is basically telling you how much of the power that we're using to power a data center, how much of that is going to the servers and how much is going to the cooling and everything else. And if you have 1.1, this means 10% is going to the cooling. The rest, or let's say if you have like 100 watts to the server, then 10 watts goes to the cooling. So we have a 10% overhead for cooling, etc. An ideal setup would be everything goes to the servers, which does not include the cooling within the server, just includes the cooling outside, right? So just basically the building, etc. And so this, for example, this would be like your laptop usually doesn't need external cooling. So there we would have like a 1. Otherwise, in data centers, of course, like getting to 1 is very hard, but people are trying to get lower and lower. So you can get actually fairly low. However, if we make a car analogy here again, in a car, the typical AC will increase the fuel consumption by 10%, which would be like a utilization effectiveness or usage effectiveness of 1.1, right? So 10% go just to the cooling, but this doesn't say anything about the fuel economy of the car, right? So this just says, oh, I'm using so and so much for cooling on top, but it doesn't say if my computation is actually efficient or not, right? It basically just says, okay, the data center itself, the cooling is fairly efficient, but the computation might be arbitrarily bad. And if we look at this from a larger perspective, right? So this is fairly recent data from the US, where they basically, like this is like official governmental data, where they say at this point in 2024 or in 2023, they're estimating the amount of power going to data centers, just to data centers at 4.4%. And it's predicted until 2028 to go up to 6.7 to 12%. So in the best case, 6.7, in the worst case, 12% of the total amount of energy utilized in the US, right? So, and then of course you have to think about, like, if you're utilizing so much energy, if you're optimizing, like whatever you're optimizing, if you're using a larger and larger share of the energy of the country, well, there's no, like, it's not going to be efficient anyway, right? So, I mean, this is basically, even if you're, like, there's all these claims computation can like make airline industries more efficient, can like do this more efficiently than that. Let's let AI solve basically our climate problems. Now, today, the cloud already has a higher carbon footprint than the airline industry, right? So basically, just the amount of computation that's used there. I mean, there's no good way to basically offset that anywhere in the airline industry. We cannot optimize so much that these 12% or something will basically be offset in something else. And all major cloud providers today are missing their carbon reduction targets and actually increase their footprint. And to their calculations, actually, the major contributor is just hardware deployment, because they all buy certificates for the power. So it's basically all based on hardware. So, and then based on this, we kind of thought, okay, can we do something to improve the hardware efficiency, right? Can we do something, or like, what does this mean in terms of hardware efficiency, looking at the hardware trends so far? And so for this, we did like a small study where we looked at the ecological efficiency of database server life cycles. And it's something that all, like, the whole group basically chipped in, and we basically did a large scale, well, not large scale, we did an analysis of different kind of CPUs and their performance improvements over the year. And just to give you like a rough first idea, we started basically with Intel CPUs, because that's something for a long time, this was basically used for all kinds of cloud servers, and also for a lot of database benchmarking, right? So a lot of database benchmarks that you find are run on Intel CPUs. So you have good numbers to compare over the years. And here are basically the two extremes that we have in our lab. So we have like quite a few different CPUs here. And this is basically 10 years apart. We found like a Intel Xeon from 2014, has 130 watts thermal density power, 551 square millimeters, and like a thermal density power per square millimeter of 0.24. And then we have a fairly recent one with 350 watts. It's 4 times 472 square millimeters, so it's 1900 square millimeters actually, so quite a large chip already, and has a thermal density power per square millimeter of 0.18. And so in general, you have to think about this like this, right? So the older CPU is actually quite a bit smaller than the new one. And you can actually see it's 4 times, right? So these are 4 chiplets. And this is really done because it's much cheaper to manufacture smaller chips than larger chips, because larger chips, the yield is getting lower and lower. And it's also, you have less configurability. So essentially, when you're building chips, you have like a wafer, and like there will be lots of chips printed on that, or printed on a single wafer, and a certain number of those will be broken just because of like production processes. Now, the larger the chip, the relative ratio of these chips is that are broken is larger. That's the same thing I recently learned. It's quite interesting. Same thing if you think about high bandwidth memory, right? So the memory is basically high bandwidth memory stacked, multiple layers, and essentially they only know if the chip is good or not after manufacturing all the layers. So per layer you might have like or per individual chip, you have a certain yield. So a certain number of, or a percentage of the chips are broken. If you stack them, this is just multiplying, right? So if you basically have, I mean, say hypothetical yield of 90%, if you have, or 0.9, if you have 2 chips or stacked on each other, 2 layers, this will multiply. So you have 0.9 times 0.9, which would be 0.81 or something like this, right? So this gets lower and lower. The larger the chips, the lower. So you actually want to like utilize large, like smaller sub chiplets. So makes stuff a bit more efficient, especially in the manufacturing process. Just as a side note, if you find this interesting, I found this quite interesting. So now let's look at some trends. So we basically went and looked at different generations, even beyond what I just showed you, of Intel CPUs that were utilized for different kind of benchmarks. And here you can see essentially always the minimum, medium, and maximum frequency, core count, memory bandwidth, etc., for different generations of chips since 2011. And you can basically see the trends overall, how these chips are evolving. So we can see that really with like from, as I said, like mid 2000s on, there's no increase, no change really in frequency. And we can clearly see this, right? So over the years, it's basically the frequency was fairly stable. So some of the high-end chips basically go up to 4 gigahertz. The medium and minimum chips, they go to 2 gigahertz because it's just basically not as much how you say it? It's not as hard on the CPU as much. You don't need the same kind of cooling, so it's a bit cheaper to basically manufacture. So, but overall, this stays the same. The core count goes up, and it like dramatically goes up in recent editions, right? So while this has been like few cores in the very early CPUs, we're getting up to hundreds, in the hundreds, of course, already in current CPUs. And we can also see the memory bandwidth is going up, right? PCI Express bandwidth is going up. The thermal density power is going up. So the chips are getting larger, the chips are drawing more power. But recently, we've also seen that the thermal density power per core is going down. So per core, they're actually getting more efficient. The cores get smaller, they utilize less power. So overall, hopefully, we see some performance efficiency improvement, right? So, and we can see if we look at benchmarks, right? These are official spec benchmarks. So spec CPU, this is the standard, one of the standard benchmarks for CPUs. In there, we have spec int, which is basically integer calculations. This is one of the standard benchmarks that also CPU manufacturers will test their CPUs against. They will basically make sure that this is not bad, right? So, and we can see over the years, this is actually going up. This is basically single thread performance over these 20 years. We get a factor of 5 single thread performance improvements. So the CPU actually gets like on a single thread level faster. If we multiply this by the core number of cores, so we can actually measure this, but this is basically what it's doing. Just running this on multiple cores, the same thing, completely in parallel. We get a nice speed up of factor of up to 40, close to 50 almost, performance improvement over these 20 years. So we get like a really good performance improvement. If we if we divide this by the thermal density power, so by the maximum power utilization, and at this rate, right? So this will actually be close to the maximum utilization because that's like fully utilizing the whole CPU. Then we can see, well, since the thermal density power goes up, the improvement is still there. We still get an energy improvement, but it's much lower than actually the speed up of the performance, right? But we still get a good energy efficiency improvement. Now we tried this in our lab, right? So we basically went, looked at all the different CPUs that we can find over these different generations, and we basically compared the spec rate numbers. So this is basically multi-threaded performance for the CPU for integer calculations, and we compared it to TPCH, and we compared it to sorting. So because TPCH and sorting, these are kind of the typical database, analytical database workloads, right? So sorting as like a very basic primitive that you will need in the databases all the time. And TPCH is one of the standard benchmarks. And we can see, well, for the integer calculations, we see this kind of performance improvement, right? So this is only a subset. Here we looked at 20 years. Now we're only looking at the last 10 years, basically. And in the last 10 years, we get an improvement of 7.2, 7.3, if you want. Well, for TPCH, it's only 4.4, for sorting only 3, a factor of 3. So it's not that much anymore. And if now we think about the thermal density power increase over these years, it's 2.7, comparing the first one to the last one, right? If now we're looking at the increase in efficiency over these years, for spec we get 2.7. For TPCH and sorting, we only get like 45%, 48 or 45% over 10 years, right? So over 10 years, a 45% improvement in energy efficiency for these kind of servers. So now you might think, well, it's a simple kind of benchmark, and I see there's already a question. I'll come back. I'll answer this right away. But this is basically, we see it's like, over the years, improvement is not that great. So the question is, what is the performance? What is the experimental setup? So what we did is we did in memory. So it's TPCH scale factor 1, I think, or scale factor 10 with HiRISE. So it's an in-memory database system developed here at HBI that we're using. And for sorting, we're really using the standard parallel sorting. And Michael, you also have a question?
Yeah, I just wanted to ask you about what kind of database you used. So you answered my question.
Yes.
And one more thing is that it would be interesting to see the same results for different databases, because we did similar experiments about TPCH, and we saw huge differences between analytical databases in terms of energy efficiency when they are running TPCH workloads. So yeah, since you're using HiRISE, it's in memory.
Yes.
And yeah, and we did similar experiments for DuckDB, Hyper, and MonetDB, which are all of them in-memory databases. And it would be interesting also to see how the energy efficiency is compared to your results.
Absolutely.
Here. Yeah.
Absolutely. And I'm aware of your paper. So and it's a very nice paper and a very nice analysis. I think it would make sense to compare the two things. The important point that I want to make here is we're basically comparing across the different hardware.
Yeah,
right?
yeah, of course.
So it's basically, I mean, presumably, as long as the hardware, or as long, if, or let me frame it differently, if HiRISE is not completely underutilizing the hardware, right? So then, and which, I mean, we try to, of course, optimize here to some degree, then we should see a kind of a similar behavior. And I mean, the reason is basically, or one of the reasons that we see this kind of behavior is that this additionally, while these servers, of course, get like faster RAM, etc., the different kind of, it's not kind of scaling at the same time as the CPU, right? This is a very simple, very embarrassingly parallel problem. While here we have memory involved, like we need to access memory, and it's not as parallel as this kind of problem where we can just run many threads completely independently in parallel. And same thing with sorting, right? So sorting is a similar problem. It's not, we can parallelize it, but it's not gonna be as parallelizable as just like running integer calculations on independent threads. And this is all hardware, as Arnu is asking, this is all hardware that we have in the lab. So we basically tested all this in our data center here.
So, Tilmann, it's one up here.
Yes.
Is it really, can you really port these conclusions from like one application to the other? Like, I understand your argument that if you're trying to use to have maximum CPU use, it should be fine, but all of these databases have different ways to deal with kind of just housekeeping operations, and the load can be the load coming from those operations can be more or less important. Just
Absolutely. I mean, let me maybe put it this way. This is kind of the best case, right? So this is basically we're fully utilizing each of the CPUs. If we're not utilizing the CPU, a CPU, or like we do some other stuff in the meantime, right? The CPU will idle, and a larger CPU will just draw more power than a smaller CPU. And in general, right? So or just like a larger server will just draw more power than a smaller server. So in general, like the assumption of fully utilizing this at the peak load, that's kind of, I mean, there might be some things where I can utilize stuff better, but of course here we also optimize, right? So we basically also, in the sense of we compiled everything with optimization flags, etc. So hopefully and also this one, right? This is like a standard library. Hopefully this is optimized for each of these servers. And the same thing is of course true here. So meaning this is the best case. If I'm not utilizing my server and I have just a beefier server than I used before, I'm just gonna, like my energy efficiency will even be worse, right? Does make sense? Okay, so let me like switch gears a bit to, I mean, this is just one aspect, right? So we're talking about energy efficiency here. There's an energy efficiency like is one aspect, but then there's also like carbon efficiency. And carbon efficiency is something that has to be basically calculated by location. And just because I was at University of Toronto, I picked Toronto. I could have also picked McGill. This might have, or maybe both or something. Yeah. So I just basically looked at the power plant map and electricity maps and checked what is the carbon intensity of power at the University of Toronto, roundabout. So I mean, in general, in Ontario, if you look, it's going to be 53 grams of carbon per kilowatt hours. So that, and that's a very low, actually, that's a very low grid carbon intensity. This is what we call basically how much carbon do you have per kilowatt hour. And this determines the operational carbon intensity. And this is mostly because Ontario uses a lot of nuclear energy, right? So a lot of energy comes from nuclear and also from hydro. So these are two low carbon emitting energy sources. And also Ontario calculates a very low factor constant for nuclear energy. But I mean, also if you look closely, right, the University of Toronto is somewhere here. The closest energy source, and physically energy is always drawn from the closest energy source, will come from here. And this is actually a gas-powered plant. So this is basically, and this usually has something like 500 grams per kilowatt hour. So physically, University of Toronto probably gets a lot of power from here. And this is, you can also see, this is where major kind of carbon emissions in Ontario come from, is from gas. Although most of the power does not come from gas. And this is because if everything would come from gas, it would be 500 grams per kilowatt hour. But since gas is just such a high intensity, this is where most of the emissions come from. If we now look at this or we compare it, so how much does such a CPU now take, right? If we could look at the Intel, the latest Intel that we are testing, this is like 20 grams of CO2 per hour roundabout. So that's basically something like 5 liters of gas per week around. So if you compare it to driving a car again. And the nice thing is you can actually also look all this up, right? You can see Ontario is actually doing quite well in comparison to many of the neighboring states in the US, where there's much more gas and sometimes coal power. And Germany, for example, would have something like 340 or 350, because Germany still utilizes a lot of coal power. So that's the operational carbon. So this way we can basically calculate how much does the server utilize while we're using it. But another aspect is embodied carbon. And this is basically carbon that comes from the production, the transportation, and end of life. And this has an increase in impact. And this is something that I will show you, is basically how this basically increases over time. Or how this basically, what kind of factor this has. And in a very simplified model, you can basically say the server footprint is the embodied carbon plus the operational carbon. And the operational carbon is basically you're utilizing the CPU. I mean, in general, it would be basically how much power goes into your server. If you're in the cloud, you would basically, or in a data center, you would have to add the cooling on top. So you can basically multiply this by 1.1, 1.2, something like this. Typically, you cannot directly measure this. So what we did, we basically use the CPU times the utilization. Then we add on top DRAM and SSD and multiply it with the grid carbon intensity during the operation. Again, this is a lower bound basically, because on top there would be maybe additional cooling, there would be the power supply, there would be other things that basically additionally draw power. Then on the other end, we have the embodied carbon. This is basically how much goes mostly into the production, right? Transportation has some impact, end of life has some impact, but the major part is the production. And here we're basically looking at the materials that need to be procured. So in order to basically have silicon, you need to mine it. You need a lot of, like, in the process of manufacturing CPUs, you need like energy, and you have like a lot of additional greenhouse gases that are produced. So, and here we're looking at the grid carbon intensity during the production, because usually chips are not produced where they are utilized, but they are produced somewhere else. So either by Intel in the US or by TSMC somewhere in Taiwan. And there, the grid carbon intensity typically is higher than what you would have in Ontario, for example. And then we would divide this by the yield, because as I already said, typically not all of the CPUs that you're generating or that you're building will work, but there's like a certain factor of CPUs or a certain amount of CPUs that will be broken. So this is our simplified model that we used. And with this, we can basically calculate how much power or how much carbon goes into production, how much carbon goes into running the server. And with this, with utilizing our performance measurements, we can say, when would it actually make sense to replace a server? Or after which amount of time, if I replace a current server with a new server, this will be offset, right? So when will my new server have produced less CO2 than just keep the old server running? And here I did the math for 2 servers. Basically, we have like 1 generation or close to 2, like 1 generation to the next. So it's basically 2 generations, 2 AMD servers with like very much the same kind of hardware setup, but the newer server is a bit like the newer CPU has a bit faster RAM, so gets a bit better performance. We're utilizing the spec int So this is, again, best case where we get best performance improvement. And I'm utilizing the Ontario kind of setting with 53 grams of CO2 per kilowatt hour. And if we say this, so our calculation basically tells us we have around about 200 kilograms of carbon for the new server. The accumulated CO2 by running this server will only be offset after 7.8 years. Such that if I just continue to utilize my old server, then like if I just continue to utilize this will basically be slower. So it will consume relatively more energy than the new one, but only after 7.8 years, this actually pays off, right? So I would have to run the new server at least for 7.8 years, ideally longer. Otherwise, I'm going to just produce more CO2 than if I utilize the old server. Now that's one example. Now let's look at a country that has even lower grid carbon intensity, namely Sweden. In Sweden, there's 25 grams per kilowatt CO2 per kilowatt hour. And if we're now utilizing the server even a bit more, so we're doing sorting, so meaning the newer server will be even faster and more efficient. And we're taking two servers that are 10 years apart from each other, right? So here, the new server should be way more efficient because we have like a lot of performance improvements over the year. And here we do the same kind of math, and we can see it basically only pays off after close to 17 years to replace the server. So this basically means, I mean, from a practical point of view, you should never replace your server anymore, right? From a practical point of view, essentially the ecological lifespan of servers increases. And I mean, cloud vendors also have seen this. And this is also, at a certain point, it's also an economic point of view, right? So there's like a CapEx cost and there's an OpEx. So how much does your server cost in comparison to the amount that the energy costs? But also they want to improve their, at least for sometimes they had good carbon improvements goals. And because of that, clouds target longer lifetime circles, right? So if you really want to utilize your server from an efficiency or ecological point of view, you have to basically run it very long, much longer than anybody in the past would have told you. And it actually makes sense to repair hardware rather than replacing it. And in Europe, there's actually a right to repair because people basically saw it doesn't really make sense to throw away hardware after a certain point of time. But this is only for consumers. And for businesses, this does not cover, right? So servers are not covered, which really doesn't make any sense. And from a practical point of view, there should be a right to repair for, say, 10 years at least for servers. And we also see that the replacement of hardware does not really improve performance very much. So software needs to become more efficient. And well, this also means we really need to build more efficient systems in the end, rather than building like more like larger software or something. We really should basically think about how can we fit more stuff on a single server, right? How can we, like, the servers get beefier, get more cores? How could we put more workload into these servers, condense the workloads more rather than scale them out more? But I mean, just building more efficient systems won't really help you much, because this is quickly eaten up by Wirt's law and something that's called Jevons paradox, which basically says, well, if you're building more efficient systems, people will just use the systems more rather than be happy that they're utilizing less resources. Say, and a good example would be, well, I'm building a more efficient system. Now let's put in more AI models or more AI agents in there in order to get something a bit smoother here. This won't make stuff more efficient. So in the end, we should really try to measure and reduce or cap the consumption per user or per IT in general. right? So, I mean, and the big question here, of course, is always like, will AI come to the rescue for this? I mean, maybe there's also research on your end in this. And there's a lot of papers that go along these lines, right? One more famous one was, Bill, if you're doing AI writing or illustrating, this is much lower than doing this by hand, right? So an AI model can be 130 to 15 times produce 1,500 times less CO2 per page than a human writer. So it sounds nice, all right? But at the same time, if all of a sudden you're creating 1,500 times more pages, you're not winning anything, right? So, and that's usually what's basically happening. And then, I mean, you also hear people like the former CEO, Google CEO saying that, well, let's not think about climate goals anymore. Let's just unshackle AI, and then they will basically solve global warming. But again, this is not the model, right? So AI and the cloud have a business model that's not about efficiency, but about expansion, right? So it's basically creating larger and larger models, building more and more data centers. And it's basically right now it's an investor's arms race. And I think regulations are required. A good example is Elon Musk's or xAI's power data centers, which are basically powered by the dirtiest data energy generators that you can find, right? So they are using emergency power generators in order to power the data centers. And even if they're offsetting this, right? Even if they're buying carbon offsets to reduce or to basically greenify their overall footprint. I mean, still this is energy that is produced, will be consumed, and it's basically CO2 that's produced, right? So, and this is much more inefficient than utilizing something else or just not generating this. Okay, so overall, as a takeaway from this, right? So hardware is not improving as it used to. And this is something we can directly measure, right? We can see that the hardware, it's still getting fast, but it's not getting faster as we were used to. Just by basically saying, let's go for the next better server, we're not going to get good performance increases. I mean, we can always kind of tweak some things here and there, but from a carbon efficiency point of view, this is often like a negative thing, right? So we should utilize and make sure that we can utilize hardware as long as we can. Not always, right? Sometimes it actually makes sense to replace stuff after a certain amount of time. But for general servers, this doesn't really seem to be the case anymore. So we really should utilize stuff further. And improvements are really required on all levels, right? And unfortunately, the industry is not working in this direction anymore, right? So right now, it's really, industry is just about building more and more data centers, larger data centers, building nuclear power plants to power more AI models. And I mean, however you count it, right? Just there's no carbon neutral source of energy. I mean, there is always a certain carbon price tag to any kind of it, be it solar, be it wind, be it hydro, be it nuclear. So utilizing more of that won't make you more efficient and won't make you more carbon efficient in any way. And with that, I'm happy to take questions, additional questions you might have. Yes.
Hi, this is Isam Mansour. Really, thank you very much for your very interesting talk. Actually, I would like to ask, how do you see the opportunity actually of saving energy from the systems that is performing training or inference of language models?
So of course there's always potential to save energy, right? So to make systems more efficient. And so there's this very basic rule of thumb to say, I mean, you make a faster code, you write code in a way that it utilizes less resources. This will be more efficient. This will also consume less power to some degree. This holds. At the same time, you also have to think about like what will this be utilized for, and there's an increasing, let's say, upfront cost, right? Especially, I mean, there's basically the same problem if you think about it with buying a new server is training a new model, right? Training a new model will have a certain carbon impact or energy impact. You need a lot of power to train this. So you basically have to set off or trade off between when does it actually make sense to retrain a model? Like when does it make sense to improve a model? How much power do I need to put into this before this will ever pay off, right? So how often do I need to use this? And you often see these calculations, well, you know, if everybody would use this improvement, then we would reduce power consumption by a factor of something. But the question is like, how long would they use it, right? So how often would we have to retrain something? So there are factors, like there are always improvements that you can make, right? So say, for example, you can distill models, you can make them smaller such they fit smaller GPUs. I think from a more practical question, you can also ask, should I actually utilize a model for this, or can I use something simpler, right? Sometimes it might make sense to not utilize a model, but just like a simple linear regression or like a very simple decision tree or whatever, or nothing, right? So, I mean, a lot of software is just really, really inefficient. And I think this is, at least from my perspective, from a sustainability aspect, in many cases, the question is, where could we actually reduce the amount of computation rather than just add more
computation? Yeah.
Does this answer your question?
Yes, absolutely. I would like to thank you. I would like to add here, in the recent report from Gamma 3, Google, reported that they managed using Gamma 3 to actually support workloads in one GPU instead of 36 GPUs using DeepSeek, which showing the point that you have been describing in the answer. Like there is a lot of potential that we can optimize these systems to use less resources and achieve comparable performance.
Absolutely. So at the same time, I think you also need to basically go a step back. I think sustainability, you really have to look from a very high abstraction point, right? So, I mean, saying like on any model, okay, I can tweak here another 10% or another 50%, even a factor of 2. The question is, well, how much did I utilize before and without an LLM? And how much improvement do I get with the LLM, for example? And was this worth it, right? So is this actually worth it? I mean, this is basically my side note to this, right? So if you think about, if your task is keep a teenager busy for an hour, right? What's the most efficient console to do this? And I mean, this is basically, well, if I go to the PS1, this is 10 watts, right? And there's no cloud functionality whatsoever. So this is really just the 10 watts. If I go to a PS5 or something, this is 200 watts, plus it will constantly stream everything to the cloud. So, and from a sustainability point of view, I mean, yes, you will have like better graphics, etc. there. But if the task is just keep your teenager busy, then, well, we should probably move more towards that direction. And I mean, even just taking all the advancements over these 25 years or 30 years now, right? We could build much more efficient consoles if we were just not doing like arms races on all ends to just have larger and larger things. And better computation rather than just make stuff more efficient, right? For sometimes, and it's a while ago, but when I was interested, or when I started getting interested in computation, it was all about efficiency, right? So it was all about getting things much faster in very constrained resources. And today, nobody thinks about constrained resources. Everybody thinks there's the cloud and we can just scale everything to any kind of size that we want.
Yeah. Thank you.
Okay, so there's two more. So I'll go to the one in the chat first, and then Michael, I'm gonna answer your question. So there's, do you think in database management systems we need more powerful hardware, or should we pause and rethink our software approach? I think we should pause and rethink our software approach. I think we should rethink. I mean, we should also rethink. So one thing that I've seen in, like, I've been data center, like chief or head of the data center at HBI for some times. I've seen a lot of software being deployed, and a lot of the software basically utilizing like just our campus management, right? So basically where students sign up for courses and this kind of stuff. We have a separate server, beefy server just for that. And HBI is small, we have 1,000 students. And the server is, the software is really slow. And the company that built the software told us, well, your server is too old. This is a 3-year-old server. You need a more recent system in order to run the software. And I told them, 1,000 students, this has to easily run on my phone. This is something I can have a contact list of 1,000 people on my phone. This should easily run, right? There's more than enough CPU, there's more than enough RAM in there. It's just that your software is so slow and so like utilizing the database in a very bad way, such that it is slow. Of course, I can buy a more beefy server. I can improve the performance of the database to some degree, but it will never change the fact that the software that it's utilizing the database is really bad. So I think, I mean, we need to think in a more holistic way, right? So, I mean, just by saying, okay, I'm going to build a better database system. Of course, we want to build the best database system, the most efficient one that's can, I think, have many people on the same system, right? So like multi-tenancy, I think is a very important aspect that's been sort of forgotten for some times, where I think, well, most companies, most applications won't require the amount of compute that a single server can give, right? But the way things are implemented today is usually you're scaling out rather than saying, well, okay, maybe you're virtualizing to some degree, then you get some efficiency back. But I would still claim in many cases, the amount of compute you get in like a single instance, the smallest instance you can buy, is still more than you would ever require. And by adding all the virtualization and different kind of stuffs in between and the different, like a microservice architecture, everything is just getting much more inefficient. So I think utilizing the hardware more efficiently makes a lot of sense. Utilizing the hardware for longer and making sure that the software is also utilizing whatever we're building efficiently and telling the software how to do so, that makes a lot of sense. Okay, Michael also had another question.
Yeah, thank you, Professor Rabl. It was a very nice and interesting talk. I have a couple of questions. Did you investigate the energy proportionality in your experiments, or you investigated the maximum utilization of the CPU?
We mostly used maximum utilization. So the energy proportionality, so typically server, I mean, we use this very simple model for this. So going back here, maybe, it's not exactly this, right? So we don't just go from 0 to 100% in the utilization, but our model very simply says idle power is 50% up to 100%. And then linear utilization, which is not 100% correct, right? So the typical, and this really depends on the hardware, but for CPUs, you have, it's not perfectly, I mean, it starts from say 30% idle power to up to 50 or even more percent idle power. More modern CPUs get a bit better in this regard. And then also the power curve is not completely linear. This really depends. Some of them like are more in an S shape. Some of them are more linear. Some of them like at a very high utilization might even have a peak because of some kind of turbo boost mode or something like this. So we modeled this simply. Short answer.
I see. And in this slide, for the embodied part,
Yes.
how easy was to find the information for each CPU in order to complete this formula?
Not super easy, but it's, I mean, for Intel CPUs, we basically
Okay.
did this by square millimeters. So, I mean, there's different ways to calculate this. And here, again, it's lower bounds, right? So here you can see we calculate 200 kilograms for the new server. Even official HBE numbers often go as up as a ton, right? So up to 1,000 kilograms for a new server. And this is like highly dependent. So the numbers for a CPU are like in between 12. So I think we calculate 12 kilograms for such a CPU of CO2. You can find numbers up to 280 kilograms for CPU. This is where things, I mean, we try to utilize numbers that are most conservative in a way such that like whatever we're claiming is for sure true. It's like probably it's even worse, right? So probably
Worse, yeah.
should even utilize the servers much longer because the embodied carbon is much higher.
I see.
At the same time, one also has to say, I mean, looking at this, these numbers, right? These are also like very different from like depending on like the constants or the coefficients per different kind of source of energy. They are also very different depending on who you ask. So we're basically just utilizing electricity maps, and they're utilizing like standard parameters from the UN, or in this case, like Ontario, there's a paper written, I don't remember, 2011 or something, from University of Waterloo that estimated, say, for example, here 5 grams of carbon per kilowatt hour for nuclear, which is much lower than any number you would find anywhere else. So what we're utilizing those basically to stay on the safe side. But presumably, my assumption is this needs to be higher. Also, the embodied carbon needs to be higher. So in the end, it kind of evens out.
Okay, thanks. And one last question. In your experiments, did you observe a linear relationship between the performance and the energy consumption? For example, better performance, less energy. Did you observe a linear relationship between these two metrics?
So no, right? So I mean, it's not a linear. You can see that it's not perfectly linear, right? So you can see this in these two graphs. Here you basically see the performance of each of the CPUs in the sense of like if you're million tuplets per second, runs per hour, or result score in the benchmark. And here you see the energy improvement, right? So it's basically divided per watt that is utilized by the server. And you can see for some, it's kind of linear, but it also does not necessarily always hold the case, right? Some CPUs might have like a slightly different or completely different result to that. So you cannot just basically say this CPU is 3 times more performant, so it will utilize half of that, like 1.5 less energy or something like this. It's really dependent on the hardware and on the application.
And this improvements in the energy efficiency is because of the hardware improvement. You used the same software.
Yes.
In all the experiments. Okay.
Yes. Okay. So this is really just it's same setup, same like different hardware, same software.
Okay. Thank you very much, Professor.
Okay, so just being mindful of time, I think we should end this session here.
Okay. Yeah, thanks for the questions. Happy to receive. If there are any further questions, feel free to reach out, right? My email is here. You can also find it online easily. And thank you very much for giving me the time to present.
Thank you, Tilmann. Let's thank Tilmann one more time. This was a super interesting talk. Thank you all
Thank
for
you very much, Tilmann. Thank you. It was a great talk.
Thank you very much. Take care,
Thank you very
everybody.
much, Tilmann, for also like the whole coordination was super easy, and thank you for making it very quick. We've arranged it in a very short amount of time, and that is thanks to you.
Thanks a
And
lot. It was a pleasure.
yes, I will stop the recording now, and thanks again for the talk. Have a great one, everyone.